Now that we've thought a little bit about how or what scales we should be representing things at, how we can represent different features, let's get down to the comparative pieces here. Vector versus raster. Earlier in the class, I gave you the vector pitch, can give you the raster pitch now. Here's raster data. On the right, raster data is pixels in a grid. You can see points, lines, and polygons or areas, but that doesn't really matter. It's not how it's structured. It's a pixel in a grid. So everything geometry-wise comes down to those cells, those pixels. Lines look a little jagged. Points are represented by one cell. Areas. This is not a very good example. It's from a book by Paul Bolstad, one of the classics of Intro GIS. Paul Bolstad's Fundamentals of GIS Essential. If you need a GIS textbook, really useful example of an area, a rectangle. You could do something more interesting to show the kind of stair-stepped raster. Oh well. Same data represented two different ways. But what are rasters good for anyway? Well, I'm going to be team raster here today and try to pitch you on raster data. Raster data has a really simple data structure. Whereas vectors are complex and require some kind of specific specialized editing software to edit, raster data you can edit in a text editor, Notepad. Want to change your raster data? Go to Notepad. Want to fix some kind of error that you see? Go to Notepad. Now, hardly anyone does that anymore, but that simple data structure means that raster data is really interoperable. You can use raster data in lots of different programs, in lots of different software, in lots of different contexts. Has a lot of different utility. Now, raster data is very large, especially if you're storing millions upon millions of cells, but it's easily compressed. Sometimes you'll download raster data and it's compressed twice, because that's how much you can compress your data to be able to save disk space. And then you unzip it somewhere else and everything gets out of control, but that's part of the fun. There's no really good way to spin the coordinate conversion with raster. Rasters belong in whatever coordinate system they have come to you in. Please don't change them. Changing them causes problems. Raster analysis is really easy. All data in raster data is continuous. So you have a whole surface that you can use. It's very simple to do raster calculations. We do raster calculations in Lab 7. It's really fun. It's math with maps. You can add them and subtract them and divide them and do whatever you want to them. Hey, simple mathematical functions, complex mathematical functions, doesn't matter. It's really direct and really easy to use with. Precision of raster data is just what cells you have. What size cells? 10 meter, 50 meter, 30 meter, 1 meter. Great. That's what you have. No difficulties there. Mentioned this before, but raster data is really accessible to use. It's easy to modify, easy to work with. And rasters are images. So if you need to show a beautiful satellite image of the landscape or topography, a lovely hillshade, that's what rasters are. So they're quite nice to work with. Just don't zoom in too far. Raster files, so however you get pitched on them or however you use them, eventually you will have a raster file. Well, okay, how did you make it? How did you create this raster file that you have given to me? Well, in some cases, they are sensed. Remotely sensed imagery has some kind of sensor that is measuring electromagnetic energy, and we'll talk about that in a future recording at the end here. And those sensors have certain resolutions. They have certain sensitivities. So they sense at a certain area and it's converted to data, and then you get a pixel. And the satellites do that forever. But sometimes it's more difficult to convert the real world into a raster, or you have to make decisions about how to convert the real world into a raster. This is occasionally automatic, It is occasionally coded or scripted. It is occasionally decided by the user, decided by the analyst. But those decisions create the logic or create the workflow that then allows a raster to be made. If we are calculating elevation, if we are calculating land cover or precipitation, any of these kind of things, we have some kind of logical process that has been created to then organize and create our raster data. All of these decisions then go into determining that file structure. So here's some elevation data. See our lovely contour lines at our different elevations. So our roughly 10-foot contour lines here. So if I were to click on any point here, I could see that it's, okay, it's some value. Okay, right here. Let's try this one. I can see that my contour lines are actually crossing. There's a lot of different ones. So I've got 895, 905, 925. But the pixel value, the raster value underneath this kind of red hue here, says it's at 950 feet of elevation. So again, we're dealing with raster data, which can only have one value per pixel. And this surface of raster data then gives us a difference of understanding what the landscape or it looks like than our vector data. The vector data says, oh yeah, there's a line here, there's a line here, there's a line here, there's a line here. The raster data says, nope, there's one cell and it's 950 feet in elevation. We get that out of the way. We can see the full landscape again. So again, the raster has one value per cell because often we need to represent elevation as a continuous raster to do climate modeling or surface modeling or anything like that. Whereas the vector data says, well, okay, here are all of the different contour lines. So at some point, some decision was made to essentially, I don't know, take the maximum or take, it's definitely some high value, right? Because 950 for that cell is definitely on the high end, 935, 945, maybe 955. Yeah, that's high. But someone decided, okay, this raster is going to have high elevations, which is fine. The whole thing is consistent and that doesn't bother us. So there are lots of different data methods to choose this. This is generally referred to as the mixed pixel problem. It is a known and outstanding, question in the whole world of raster data and remote sensing and GIS. And as long as you have a clear decision-making process and a consistent decision-making process, really any of these options are valid as any of the other ones. It's just about making the right decision for your data. So we have a centroid method, assigns each cell the value of the feature at the center of the cell. So whatever's in the middle wins. We have winner takes all. Whichever feature has the highest percentage of coverage in the cell wins. So we can, oh, that cell is mostly water. It's a water cell. We also have dominant decision-making. Important types win. Well, water is dominant. If there's any water in the cell, that's a water cell. And these conversions and these classifications or these reclassifications are really important for different uses of the raster data, different structures, different functions. If you're really interested in water and hydrology, you might choose a water dominant reclassification. Oh, I've got this satellite image. I'm going to reclassify it into land cover type. And I want those land cover types to be water dominant. If there's any water in that cell, it's got to be in my reclassified raster. Or maybe you're just trying to, figure out what has the best coverage. And so you might say something like, okay, well, I'm just interested in whatever is the highest percentage. So whatever's 51%, turn the pixel that way. Lovely landscape here. Upstate New York, Adirondack Park. Let's classify it. Ooh, fancy. Let's do that again. Pick your favorite part of the map here and watch it change. It's going to change. Ooh, let's do it again. Pick your favorite part of the map here. And let's watch it change. There it goes. Whee! The extent of my PowerPoint animation skills. One more time. Pick your favorite part of the map and watch it change into a classified pixel. So this is a satellite image. This was taken to look photorealistic. And now we're going to classify it into land cover. Ooh, now we're in land cover mode. Yes, the color scheme is weird, but that's part of the fun. So our lakes are pink. Who cares? We can see that our landscape has been carved up, and some features show up, some don't. Let's zoom in a little bit. All right, now we're in one of these lakes. Pick a favorite pixel. Ooh. Now here we're starting to see how this satellite, or I think at this level, it's an air photo at this point, but this aerial photo, we can resolve a lot more features than is on here, right? So we're starting to see some of the choices or some of the differences or some of the inconsistencies that might pop up. If we're still thinking of this lovely pink as water, which I would agree it's water, one of the things that always pops out interestingly to me is this island here in the center. I am going to get out the pen and I'm going to draw. Check out this island here. That is what I'm interested in. This one. I always feel like it's offset in the land cover. But I don't know the rules that it's making. Whoops, I really feel like, I don't know. I don't know the rules that are being taken on here. Some kind of processing is happening and it's offsetting this island. It always bothers me. But if this is applied consistently throughout the generation of this land cover image, then that's fine. But it gets back to that idea of GIS as an abstraction of data. That could be a theme throughout all of the videos throughout the entire semester. GIS is an abstraction of data, and we just have to deal with the times and the cases where that abstraction makes us kind of wonder, why are you doing that?